Full screen.
That was great.
All right.
Okay. So Emily also had all the fun facts I had about epibatidine because I only wrote down a few, but I do know that it is potentially a replacement for morphine as a painkiller because of its analgesic potency. So it is very dangerous, like nicotine, but it also could be used as a painkiller. So, more you know.
That's true. Yeah.
This paper on the synthesis of epibatidine was published by the Armstrong Group in 2007, and it looks like this. And there's one interesting step that I put a star over that's really super weird, but the rest of it, except for, again, this step down here, is pretty self-explanatory, so hopefully. Oh, wait, hold on. It won't let me do that. Cool. So the first step is called an ammonative rearrangement, and it was actually published by Armstrong, like his last name, in a previous paper in 2004. So he cited his own reaction to use in the first step of the synthesis. So this molecule right here is called T-chloramine, and it includes this like sodium counterion here. And what happens is that the negative nitrogen is able to kind of form like a weird version of an epoxide with this double bond here. And you have like the whole tosylate group on the end. And then what happens here, I don't understand why it does what it does, but you can kind of break this ring. So this methoxy group forms a double bond here to make the oxygen positive. This kind of bounces over to make a double bond there and break the 6-membered ring. And then the 3-membered ring, this weird epoxide group, is also broken, making the nitrogen negative again. So I don't understand why this is the way it is, because technically you're adding more formal charges, so it shouldn't be as favored. But then you're able to close the ring, making a 5-membered ring with the nitrogen in the like kind of the bottom portion by this negative nitrogen using one of its lone pairs to attack this carbonyl carbon and move the electrons back onto the oxygen methoxy group to reform it. And then this hangs out on the end as an aldehyde. So that's pretty cool.
Yeah, that's a great reaction. So that sort of spring-loaded second step is certainly driven by
The ring strain?
just opening that ring strain. And the other thing, like, I don't know if you all sort of noticed that this just keeps happening, that we're seeing a lot of reactions at carbons that look like acetal carbons. So in that middle molecule, the second molecule, there are 2 such atoms, meaning that it's an sp3 hybridized carbon that's bonded to 2 electronegative elements. So on both sides of the oxygen that's in the ring, both of those are acetal-like, and those are just very easy to manipulate, particularly if one of them is in a strained ring, right, that you can open it. So that probably has a lot to do with it too.
Yeah, and then this next step is just a Grignard. So you're able to use this magnesium bromide group and turn the aldehyde. Here's the alcohol that's left over. And this is actually a mixture of diastereomers, but it didn't say that which one they wanted to proceed with. It just said this is a mixture. So that was interesting. This one is also kind of weird. It's the Prins reaction and pinnacle rearrangement, but it's like a variation on the Prins reaction. The Prins reaction is usually an addition of an aldehyde or ketone to an alkene or an alkyne, but this is an ASA Prins reaction because it has a nitrogen instead, so it proceeds a little differently. So this, stannum tin chloride is a Lewis acid, and it removes this methoxy group, so you get like this positive charge over here. And then this double bond is able to take its electrons and form a very weird looking chair with actually 7 members in the bottom. So this is the ASA Prins reaction. Usually this would be this double bond would be adding to an aldehyde or a ketone, but it's able to proceed the same way, just with the nitrogen instead. And then the pinnacle rearrangement this is another variation of it because it's usually converting a 1,2 diol to a carbonyl compound. You're still getting a carbonyl compound in the end, but this is not a 1,2 diol. Instead, this oxygen is able to plug one of its lone pairs into a double bond, and this is kind of like an alkyl shift if you think about it. This carbon is now forming a bond with this one down here, so the ring that once was 7 members is now 6, so it looks like a normal chair. and the aldehyde just kind of hangs off the end. So that's like a really interesting shift. It was kind of hard to illustrate in arrow form. And I know it's kind of hard to like visualize too because the ring's getting smaller, but that's kind of interesting. And then, like I said, the pinnacle rearrangement and the Prins reaction, these are both variations of those two common reactions that they're able to use to their advantage.
I think, Beth, I think you're missing a carbocation in that fourth structure.
Is it?
Do you see what I mean?
Oh, yeah, this one here?
Yeah,
This one should.
Yeah, I think there's a carbocation right where your laser pointer is,
Yep,
which
I
is,
just noticed it on my drawing.
yeah, that's what's promoting that alkyl
It allows.
migration. Yeah.
So there's a positive charge here. I just noticed it in my little picture that I drew. But
Yeah.
sorry about that. That makes this make a little more sense.
Yeah. These are, yeah, I mean, you know, I think, not to butt in too much, but like in this reaction and in, well, I guess a lot of these, right? Every individual step is like maybe a little bit reasonable and a little analogous to maybe something that you know, but like the overall transformation, you probably wouldn't be able to predict. Like if you just look at the starting material and then look at the product, it's like, hello, you know what I mean? So like these are kind of cool. I don't know, they're kind of cool reactions. And I think, Beth, did you mention that, or somebody at some point said the person used like their own reaction that they invented?
Yep.
Yeah, was that you earlier for
That
the first step?
This one.
Yeah.
So they wrote a paper on this 3 years prior and then used it again.
Yeah. So what sometimes people do is if they invent a reaction and it works pretty well, they only make molecules that they can use that reaction to make. Do you know what I mean?
Yeah.
Yeah.
Okay.
Anyway, go ahead.
So this one is something we learned in Orgo 2. It's just a Jones oxidation from this aldehyde to a carboxylic acid. So that we've seen that. It's cool. And then this one is another new reaction that I had never heard of called the Hunz-Dieker reaction. So this carboxylic acid that we just made is deprotonated by mercury oxide. And then, like we learned in both Orgo 1 and Orgo 2, light can break diatomic bromine into bromine radicals, which can be used to do cool things. So I have my single-headed arrows, and then one of the electrons from this oxygen bump out, and then this bromine radical can bump out to form a bond between the oxygen and the bromine. And then right after that happens, it breaks, and it has this interesting resonance form. So you have your bromine radical that just left, so it makes a bond, and then it leaves to allow for this to happen. So there's a bunch of single-headed arrows happening. So one leaves and makes this carbon a radical. The other one forms a bond here with this radical that was on the oxygen to form carbon dioxide that leaves in this step. So you make this carboxylic acid in the previous step just to decarboxylate it in the next step to add a bromine. So now you have a carbon radical and your bromine radicals that are in solution, and they form a bond. And you get a 1-to-1 ratio of exo to endo. But what's interesting is that in the paper, they didn't show preference for one over the other, and they are able to perform the next reaction on both and get relatively similar yields. So that's kind of interesting. At least it was a 1-to-1 ratio, and they could use both, so that I guess made it better.
That's good.
So this is the addition of a Bach protecting group, which I think, Emily, you've had in the past, right? So this is ditert-butyl carbonate, which is what makes the group, and then phenol, hydrobromic acid, and then sodium carbonate. So you're just able to add this Bach group where the tosylate group was, and it goes right there on the nitrogen, so that's what it looks like instead of just the abbreviation. And Bach groups are used to protect amines. So tosylate can apparently also be used as a protecting group, but it was needed for the first step and the first step only. And now it's just not needed anymore, so they added a Bach. So this is a Suzuki cross-coupling reaction, and as I noted here, I don't know how this works, but we will learn it later. But what's interesting about it is that it's a variation of the Suzuki cross-coupling reaction, because in a regular Suzuki, you have the organoboron species, which is right here, so that's good. A halide, which I assumed that could count. and it's usually
No, the bromine on the other partner.
oh, that's okay,
That's
got
the
it.
halide. Yep.
And then it's usually catalyzed by palladium and a base, a palladium catalyst. But what's interesting about this one is that it's a nickel catalyst. So this is bis-cyclooctadiene nickel. So they use this instead of palladium, which is really interesting. And they tried a few different ways to actually add this group onto where the bromine was, and one of them was avidig. So they made this into an alkene, and then we're able to add like a different species with like 2 nitrogens here and 2 extra chlorines, and it worked, but not with as much percent yield. I think it was about 56%, whereas this was a bit higher. So I'm not really sure how this cross-coupling reaction works with a nickel catalyst instead of palladium, but it's just able to form a carbon-carbon bond and like eject this boron species and like kind of switch the bromine. So,
but what you might notice is this is very analogous to Emily's, right? Where that aromatic ring with the nitrogen and the chlorine, in Emily's case, it was added to the same framework that was an alkene, which is the Heck reaction using palladium. And then Beth's is the same framework, but instead of an alkene, it's an alkyl halide. That means it's and the coupling partner is now this boronic acid on the sp2 hybridized aromatic ring. So that's just a different palladium reaction called a Suzuki. But they're very, very sort of similar strategy, I guess.
Yep, so that's how this group gets added on. And the last step is just to deprotect the nitrogen. I'm trying to like move my screen, but what I have there is that's trifluoroacetic acid, which is what they used. And like Scott mentioned, you can just like kind of dissolve these off with acid. And I wanted to note the pKa of it because he took Mike's Ergo 1 class, this is cardio in action, because the pKa of acetic acid is 4.76 and the pKa of trifluoroacetic is 0.23, which is a big difference. And it's just because those 3 fluorines can like use their induction to pull that negative charge away and stabilize it better, so it makes it more acidic. Anyway, that's just a sidebar, but it is able to remove the bot group and restore the nitrogen to make epibatidine.
Super. More fantastic chemistry. I just need a moment for my heart rate to settle down. Thanks, Beth.
Good work.